All right. Can you hear me? See my screen? Great. Give it a couple minutes. Right. All right. Okay, I guess we'll get started and ease into things. So last time I finished covering the GKR protocol, which is an efficient interactive proof for evaluating a circuit. Um, this is capturing the setting where both the prover and the verifier um, know some circuit and some input to that circuit, and the prover claims to have correctly evaluated the circuit on the input, and then proves to the verifier that the claimed output of that circuit on that input is indeed correct. Um, and basically, the GKR protocol applies the sum check protocol once per layer of the circuit, starting at the output and working one layer at a time towards the input. And so eventually the prover is forced to make a claim about the input alone, and the verifier can directly check that claim in linear time, basically just reading the input, and that's about it. Um, and so today we're going to discuss some other sum check based snarks, or interactive proofs, if you will. Well, let's call them snarks, for circuit evaluation. We sort of talked about them before, but I think it's worth kind of discussing them again. So I described Spartan previously. Spartan is targeted at a kind of constraint system, which is you could think of it as like a generalization of circuits, called R1CS. So today I'm going to describe actually a predecessor of Spartan called Clover, which kind of uses the same ideas and techniques, which directly applies to circuits, in the same way the GKR protocol did, and in that way we can sort of understand the trade offs between the approach in Clover and Spartan versus the GKR protocol. And then next time, I plan to discuss Marlin, which is it's a non-sum check based snark. For R1CS. And So, one kind of high level point I try to convey in this reading group, and just generally, um, it's my perspective on kind of the snark design space that I think still needs to be absorbed a little bit better is the following. So, the non-subject based snarks like Marlin are very good for verifier calls. Unlike the subcheck protocol, they have like constant size proofs, like somewhere between 3 and 10 cryptographic group elements, and that's it. Whereas the subcheck protocol is always going to involve at least like logarithmically many field elements. So something like Marlin has very, very good verifier costs, but significantly higher prover costs. And so that latter statement, that if you don't use the subcheck protocol, you wind up with a slower prover. This is sort of evidently still controversial, and so Marlin, it's very clean to see the comparison between Marlin and Spartan when they're both described for R1CS, and you can see very clearly why the prover in Marlin winds up doing more work than the prover in Spartan. So that's a good reason to kind of repeat or cover in more detail Spartan today and Marlin next time. Okay, so with that out of the way, I'll just sort of dive into Clover. But let me pause and see if anyone wants to ask any questions before we get into technical content.
Looks like no, not so far.
No? Okay. All right, great. Okay, so just a quick reminder, in case you're not sick of it yet. So the subcheck protocol, as far as today goes, you can basically treat it as a black box. It's a protocol that solves the following problem. So the goal is to sum up all evaluations of some polynomial G, where you're interested only in the evaluations over 0, 1 valued inputs. Okay, so here G is an L-variate polynomial. And again, we're looking to sum up all evaluations of G over Boolean inputs. Okay. So it's a very powerful hammer, as hopefully we're getting comfortable with. But you kind of have to get used to applying the hammer. So once you're kind of used to how to wield this thing, everything starts to look like a nail. But if it's your first time holding the hammer, it's it's not clear that actually everything is a nail for it. So yeah, let's dive in. So a reminder of what is an arithmetic circuit, and I'll keep this short because we saw this the last two sessions covering the GKR protocol. So the input to the circuit is a vector x with entries in some finite field. Let's say the length of this input vector is n. And the circuit consists of gates that compute addition and multiplication over the field. So just a little example here. So here we have 4 inputs. This gate takes x1 and x2 and multiplies them together. Let's say this gate takes x2 and x3 and adds them together, and this gate takes x3 and x4 and multiplies them together. Right, and then maybe there are later layers of the circuit that take the values computed by each of these addition multiplication gates and do further processing of them, and eventually, let's say there's just one output gate. So this is what an arithmetic circuit looks like, and let's call the circuit C. And we saw that the GKR protocol was a very efficient interactive proof for the claim that if you evaluate C on some input X, where the verifier, let's say, knows X, as well as the circuit. The claim that the GKR protocol establishes is that C of X equals Y. So here, let's say the verifier also knows the claimed output Y. Okay. And again, like the way the GKR protocol worked was it applied the sum check protocol actually once per layer of the circuit. So for this this circuit, there'd actually be like 3 invocations of sum check. All right. So what Clover is going to do is rather than applying sum check once per layer of the circuit, it's going to apply sum check just once for the whole circuit. Okay. And so Clover is actually from 2014. It was originally described as something called a two-prover interactive proof, but really the modern perspective of Clover would be that the second prover is just acting as a polynomial commitment scheme. And so really, Clover is actually just a snark. It just didn't know it was a snark because in 2014 we didn't know that this perspective of basically none of the authors of Clover, of which I'm one of them, knew what a polynomial commitment scheme was at the time. Okay, so let me describe how Clover works. Let's see. Maybe I'll briefly explain how it compares to the GKR protocol. Okay, so yeah, so cost comparison to GKR. So for Clover, because there's only one invocation of the sum check protocol, the proof size is about log circuit size many field elements. Now with Clover, there's also going to be a polynomial commitment scheme involved, and so that will add a little bit to the proof size. Say one evaluation proof from a polynomial commitment scheme. Okay, and what's happening here is at the very start of the protocol, before we apply sum check, the prover is going to commit to some polynomial, sort of capturing the value of every gate in the circuit. And then at the very end of the sum check protocol, the verifier is going to have to evaluate that committed polynomial at a random point, and the prover is going to provide the requested evaluation as well as a proof that the provided evaluation is indeed consistent with the commitment. So this is what a Clover proof looks like. And the prover time is going to be linear in circuit size many field operations, plus the time to commit to the polynomial and compute one evaluation proof. Okay. So here's the proof size, here's the prover time for Clover. The comparison is that for the GKR protocol, the proof size grows with the depth of the circuit. So it's depth of the circuit times log circuit width, but let's just say that if the circuit isn't like ridiculously big, that's pretty close to log circuit size. So field elements. And so the GKR proofs are bigger by a factor of depth. So this is one of the main benefits of Clover over GKR is smaller proofs. So Clover has smaller proofs than the GKR protocol. Okay. So as we discussed last week, there in many contexts when you use the GKR protocol, the input X is actually not public; it's committed. And in that event, which is sort of the situation that's most comparable to Clover, because Clover involves commitments regardless. There's a second aspect to the proof, which is just as with Clover, one evaluation proof of the polynomial commitment scheme. Now, an important point here, which is how important this point is, depends on what polynomial commitment scheme you use, and like how big is the input to the circuit relative to the size of the circuit as a whole. But is in the GKR protocol, let me change the color of my pen here. In the GKR protocol, the commitment scheme is applied only to the input X. Whereas in Clover, the commitment scheme is applied to the whole circuit, to every gate in the circuit. So this is one of the main downsides of Clover, is that, this can affect both prover time and proof size, is that the amount of data that gets committed in Clover can be much bigger than in the GKR protocol. Because in the GKR protocol, like even if the input is, if the input is public, the GKR protocol has no commitments at all. If the input is committed, well, the input was committed, and there's still an evaluation proof needed in the GKR protocol in that event. But the thing that's getting committed is only the input to the circuit, right? Not these interior gates of the circuit. So it's a little bit of an involved comparison, because the size of the committed polynomial can be very different between the two protocols. But and then in the GKR protocol, the proof size, the prover time, as with Clover, is linear in the circuit size many field operations, plus again the time to compute an evaluation proof from the commitment scheme. But again, this the amount of committed data here might be less, and hence the evaluation proof might be faster to compute, depending on the commitment scheme used. Okay, so that's it. So Clover, you get shorter proofs, but potentially bigger prover time because more data is getting committed. GKR protocol, you get bigger proofs, which is bad, but a potentially faster prover, the savings coming in because less data is getting committed. Okay. Let me just, I guess that is the high level comparison.
We have a question.
Question, please, go ahead.
So the question is, what do you mean with commit if it isn't using a polynomial commitment scheme? And I'm not sure what that's in reference to, hoping you do.
Yeah, I don't quite get it either. So in both cases, when I talk about
for Clover 2014.
Oh, okay. Yeah, so I said in Clover, it was described as a two-prover interactive proof. But the reason there's a second prover there at all is effectively to allow the protocol the functionality, that the same exact functionality that is provided by a polynomial commitment scheme. So it's like what is the point of a polynomial commitment scheme? It's so the prover can kind of act as if it's sending a giant polynomial, but without sending it, because if it actually sent it, the proof would be huge. And so in Clover, it's like the first prover sort of wants to send a giant polynomial capturing the value of every gate in the circuit, but because we didn't want to use any cryptography and we thought we were describing a two-prover MIP, we just didn't have that option. So instead, the prover just does its thing, like kind of acting as if it sent the polynomial capturing the value of every gate in the circuit. And the risk of that, the reason that's not generally secure in the one prover setting is because the prover can kind of change its mind. If the prover doesn't actually commit to the polynomial, it can change its mind late in the protocol regarding what is the polynomial it, like would have committed to but didn't. Okay, and in particular, if the Clover verifier is like, hey, down here when it asks for the evaluation, it says the verifier says I need to evaluate, this polynomial you should have committed but didn't. So let's call it P at R. You have a big problem. You have an attack on the protocol if the prover chooses the polynomial to depend on R. If the prover is able to choose the polynomial, knowing the one point it will be evaluated at, well, that at that point, all security is out the window. So what happens in the Clover paper is the verifier goes to the second prover, who does not know what R is, and says, "Hey, second prover, like you tell me P of R." And maybe give me a little extra data, just for me to, I don't know, don't worry about it. It's in the weeds of how multi-prover interactive proofs work. And in that way, the second prover is exactly there in Clover to kind of detect or make apparent the situation where the first prover like changed this polynomial that it wanted to commit to but couldn't, in a manner that depends on R. The second prover will sort of not know what R is and will kind of be stuck, not letting its answer depend on R. Okay, did that answer the question? Or I sure hope I didn't misinterpret the question given how long I took to answer it.
Yes, it did.
Okay, great.
And it looks like we have another question. Suvi just popped on stage.
I just had one question, Professor. So, would it be possible to intuitively describe why Clover can do away with just one subcheck as opposed to GKR, who was doing one subcheck every layer? The reason I have this doubt is because one subcheck essentially means that one variable satisfiability is being checked, and so that's the doubt.
Yeah. Let me try to see. So I don't see the intuition that one sum check means one variable satisfiability is being checked. I'm not quite sure where that intuition comes from. But what I can say, and then feel free to elaborate or clarify afterwards. In the GKR protocol, the verifier is really ultimately seeking to force the prover to make a claim about the input alone. It really needs a claim about the input alone because in GKR, there's no way to get the prover to commit to the values of the interior gates of the circuit. Right, that's exactly what GKR is trying to avoid relative to Clover. I frame that as like a performance benefit, but you could also frame it as like maybe you just like hate cryptography and want a statistically secure interactive proof when when the input is public, which is what the GKR paper from 2008 was interested in. Whereas if the prover in advance can commit to the values of all the interior gates in the circuit, somehow it's the one sum check then winds up reducing the claim, it reduces a claim about, the prover's original claim, sort of like I evaluated the circuit correctly gate by gate on this input, is a claim involving all gates of the circuit. Okay, and what the one invocation of the sum check protocol in Clover does is it reduces that claim, so a claim about all gates being evaluated correctly, to a claim about one evaluation of like the multilinear extension of like all gate values in the circuit, like both the inputs and the interior gates. Okay, and so like here's the key, and I'm not sure I have a ton of intuition to give about this, but it's like if all these gate values were committed in advance, then this claim is like fine as far as the verifier is concerned, because due to the binding property of the commitment scheme, there's no way for the prover to like, you know, mess with, like, basically the verifier is going to get the evaluation of the interior gates out of the commitment scheme and everything will be fine. Whereas in the GKR protocol, because we don't want the prover to commit to those interior gates, somehow making a claim, about one evaluation of all gate values is just not useful, because the prover, without any commitments to these interior gates, would be able to like equivocate and change, the values somehow. Or I guess another way of saying that is the verifier has no way to get the needed evaluation of those interior gate values if they weren't committed in advance. Did that help? Should I try to address why there's no univariate satisfiability going on here?
So I think I could understand that the Emily part relating to the last day's discussion. And my clarification of one variable satisfiability is that in every interaction of some check, you essentially are replacing one of the variables by a random value, right? It was chosen by the verifier. So that's why I said it that one subcheck means checking one variable satisfiability.
So it's in each round of some check, you replace one variable,
Yes.
but across all rounds, if there are many rounds, you're replacing a lot of variables. So maybe that's another, sort of explanation for where the intuition was not quite, leading down the right path.
Yeah. Thank you, sir.
Sure. Yeah. Thanks for the questions.
And I have once more too. Thanks for the intuitions you just laid out. And to continue this, I wonder if Clover and or Spartan verifier needs to know the circuit like in GKR, it's required for him to know, or does this circuit another commitment or somehow schemed and compressed?
Yeah, so it's like completely analogous to the GKR situation, right? So like, what's going to happen is, as we'll see in a moment, the circuit, the protocol like Clover or Spartan will somehow capture the circuit via some multilinear polynomial describing the wires of the circuit, and the Clover or Spartan verifier will have to evaluate that polynomial at a random point. Okay, so this is sort of this comes up over and over again in like snark design. It's like if the circuit has repeated structure, the verifier will be able to evaluate the polynomial capturing the wiring of the circuit at a random point very quickly on its own. If the circuit does not have any repeated structure at all, that might take time, like linear in the size of the circuit. And if you're not happy with the verifier taking time linear in the size of the circuit, what you can do is have an honest party cryptographically commit to that, wiring polynomial in pre-processing. And then in the online phase, when the verifier determines what point it needs to evaluate, that polynomial at, the prover can then provide the evaluation along with the proof that the evaluation is correct. So this is exactly the same thing that I said last time about the GKR protocol. It's really no different here. Does that make sense?
Yes, yes. Only the small one is the is this reusable? Like, can verifier reuse this work of a trusted party?
Yeah. So it's the pre-processing. You can use the commitment as many times as you want. So the pre-processing, to produce the commitment, to the polynomial capturing the wiring of the circuit, that only has to happen once for all time, and you can prove, as many things about that circuit as you want. So to be clear, like in the online phase, like, if the prover claims, like C of, like I know a W such that C of X comma W equals Y, and I know a W prime such that C of X prime comma W prime equals Y prime, and so you have three different claims here or whatever, right? You can reuse the pre-processing of the circuit, by an honest party to compute this commitment to the wiring polynomial, all three times. But the prover in the online phase will have to compute three separate evaluation proofs. I guess a caveat to that is some polynomial commitment schemes would let you sort of amortize, or would let you do better. If you because they have some kind of amortization properties where you can prove like three evaluations at the same price as like one evaluation or something like that. But yeah, so I think the key point you're worried about is the honest party doing this expensive pre-processing, and does that have to happen over and over again? The answer is no. It can happen once, once for all time.
Yes, it is what concerned me. The randomness, I don't know. I'm checking. That's all. Thanks a lot. Thank you.
Yeah, thanks for the question. Other questions?
That's it for now.
All right. Okay, so so let's see how Clover works. Now, I think I've like basically sketched it before, and I also think it's similar enough to the GKR protocol that it really shouldn't take long to cover. So let's just introduce these wiring polynomials I mentioned, in response to the last question. So we're going to let add and malt take as input three binary gate labels. Okay, A, B, and C. And I'll elaborate in a moment on what I mean by that. And, add of A, B, and C will spit out one if B and C. Well, how do I want to, let's see. If gate A in the circuit sums up gates B and C, and zero otherwise, and similarly malt ABC will equal one if gate A multiplies the values of gates B and C, and zero otherwise. Okay, so coming to the example here, what we're doing is we're assigning each gate a binary label. So maybe I'm just going to redraw the example rather than try to clean up that diagram from before. So just real quickly, x1, x2, x3, x4, and then but I think I had three gates, two gates, 4, 7, 8, 9. All right, let me do it this way. Try to keep everything a power of 2 for simplicity. Yeah, okay, let me just make 2 output gates. All right, so here's our circuit. So this has 3, 4, 5, 6. No, I'll make it 1 output gate, sorry. All right, so here's our circuit. It has 8 gates. So we would, let me change the color again. So we would assign this input label 0, 0, 0, this guy 0, 0, 1, and this guy 0, 1, 0. this addition gate would get label 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So that's what I mean by assign every gate in the circuit a binary label. So if there are 8 gates in the circuit, they can each be assigned a unique 3-bit label. Since there are, 8 vectors, 8 Boolean vectors, each of length 3. And then focusing on this addition gate right here, like add of 0, 1, 1, comma 0, 0, 0, comma 0, 0, 1 would be 1, indicating that this addition gate has label 0, 1, 1, and it sums up the values of these 2 gates. And similarly, this multiplication gate here would be captured by, mult 111, comma 101, comma 110 equals 1. Again, indicating that the gate with label 111 is a multiplication gate whose in neighbors have labels 101 and 110. Okay, and so this is just like the GKR protocol's add and mod function, except the GKR protocol had a different add and mod function for each layer, whereas Clover is, treating the whole circuit as just like one big monolithic object. Okay, and then finally, we're going to define W to take as input one gate label, one binary gate label, and output the value assigned to that gate. Okay, so those are the functions that I need. And again, each of them is analogous to what's happening, a function in the GKR protocol, just not going layer by layer through the circuit, but rather dealing with the entire circuit all at once. Okay, and so now here's the key claim. So like W, correctly assigns a value to each gate. And by correctly, I mean, it's actually the value obtained by going gate by gate through the circuit and evaluating that, the circuit on input X. If and only if the following holds. So let's see, add A, B, C times W of A minus W of B plus W of C plus mult ABC times W of A minus W of B times W of C. Okay, let me just pause here for a second. This claim is not quite going to be true. It's almost going to be true. So let's say equals 0, and this would be for all ABC in 0, 1 to the log circuit size. Okay, so this claim is not quite true merely because what these constraints here do not make sure that the input equals X and the output gates equal Y. Okay, so I call these I/O consistency checks, input-output consistency checks, right? The prover is sort of claiming it evaluated the circuit on input X to produce output Y, and I'm just, these equations here, these constraints do not include the I/O consistency checks. Okay, so let's forget about the I/O consistency checks for a moment, and if we forget about I/O consistency, this claim should be fairly straightforward to see. Like what's going on is, if gate A actually is supposed to sum up the values of gates B and C, then add ABC will spit out 1, right? And then this expression here, W of A minus WB plus WC, will be 0 if and only if indeed the value assigned to gate A is the sum of the values assigned to gate B and C. Right. And so, in that case, you would get 1 times something that's 0 if and only if the value assigned to gate A is correct. right? And so and you know, and if A is an addition gate, then malt ABC will be 0, and it'll kill, you know, the other term. And so what you get is that for each addition gate, you know, the value assigned to gate A better be the sum of the values assigned to its in neighbors B and C, or else, you know, this expression here will not evaluate to 0 at A comma B comma C. And similarly, if A is a multiplication gate and its in neighbors are B and C, you know, malt will spit out 1, and this expression in parentheses here will be 0 if and only if gate A is assigned the value that is the product of the values assigned to gates B and C. And so yeah, there's basically winds up being, you know, kind of one constraint per, you know, addition or multiplication gate in the circuit, enforcing that the value assigned to that gate is the correct value given the values of its in neighbors. Okay.
Question.
Yeah, question.
So you have an if and only if statement here, and it seems very obvious to me, like in one direction. So if W correctly assigns a value to each gate, then you explained why that means every term in that sum will be the whole sum is 0. But I don't see how you go in the other direction at all. Like, just because that sum ends up being 0, how do we actually know that W correctly assigns everything? Like, if we knew that every term was 0, then that would make sense that yes, W has to correctly assign everything. But if we only know that for the entire sum, I mean, how we can know that W is correct?
So there is no, just there's no sum here, other than
Okay, I misunderstood. That makes sense. That my concern is addressed. Good.
Yeah, great. No, it's a great question. Yeah. Yeah, so this is so what I'm saying is this expression here, which, you know, these are the only sums.
It's like, yeah, for each gate, that expression is 0 if and only if W handled that gate correctly.
Yeah, exactly. For each gate A, this whole thing that I just circled in red is 0, you know, for all B and C if and only if A was handled correctly.
Sweet.
Okay, good. Yeah, so this is like, yeah, it's not a super complicated claim. It's also not super clear why it's useful, because there's still this for all triples ABC here, whereas the sum check protocol is useful for computing giant sums, right? So we're still going to have to do some more gymnastics to relate, you know, this you know, this expression equaling 0 for all these tuples to some giant sum. Okay. So let's go through those gymnastics real quickly. Now, firstly, I want to, you know, because we're ultimately looking to apply the sum check protocol, you know, I define like add, malt, and W not to be polynomials. They're just functions whose domain is, you know, gate labels. So to apply the sum check protocol, you actually need a polynomial. And so I'm going to get my polynomial as usual by just taking multilinear extensions of everything. And, you know, this claim doesn't change if I just put a tilde over everything to replace W itself with its multilinear extension. And that's because, you know, this claim is only, you know, evaluating these polynomials at the Boolean inputs, and multilinear extensions by definition, you know, take the same values of whatever function they're extending if you only look at the Boolean inputs. Okay, so good. So now I have, you know, something involving polynomials here circled in red, but I still have to deal with the fact that the sum check protocol is really good at computing, you know, very large sums, but there's this for all, you know, tuples ABC and 0, 1 to the log circuit size here. So how do I go from a for all to a big sum? Okay, so let me call, and by the way, I'm just going to completely ignore IO consistency checks. If they're not complicated, like I could just modify this expression to bring in some IO consistency checks. It's just, I don't think it'll conceptually add to anything. So let's just ignore it. So let me give the left-hand side of this constraint system like a name. So let G of A comma B comma C let me define it to be, and I'm just going to write out the left-hand side here. Add twiddle A comma B comma C times W twiddle of A minus the sum of W twiddle of B and W twiddle of C, plus mult twiddle of A comma B comma C times W twiddle of A minus W twiddle of B times W twiddle of C. Okay, good. So I want to relate G vanishing, meaning evaluating to 0 for all Boolean inputs ABC to a big sum. Okay, so here's an attempt that doesn't work. So let me call it attempt 1. So like I'm calling it like wishful thinking. So what we want is that G A comma B comma C equals 0 for all Boolean inputs A, B, C and 0, 1 to the 3 log circuit size. I want this to be equivalent to some giant sum equaling 0. So here's my attempts at identifying such a giant sum, but again, it's not going to work out. Sum over all A comma B comma C in 0, 1 to the 3 times log circuit size of G of A comma B comma C squared. So this is what I would like G equaling 0 at all Boolean inputs to be equivalent to this sum being 0. Okay, and it sort of almost is. Okay, like imagine for a second that G spit out values like not in a finite field, but over the integers. So that this big sum was over the integers. Okay, then actually this equivalence would hold, right? What's going on here is, obviously if G of A comma B comma C equals 0 for all 0, 1 valued vectors ABC, then this big sum will be 0, whether you're over a field or the integers, right? Because you'd just be summing up 0 squared many times, and 0 squared is 0, and if you sum up 0 over and over again, you still get 0. Okay. Where you run into issues is the following: like if the sum were over the integers, then a single ABC Boolean ABC getting fed into G not spitting out 0 over the integers, that would be enough to ensure that this sum is strictly positive and hence not 0. Because the squaring is there to take anything that's not 0 and make it strictly positive. And so if you sum up a whole bunch of numbers, all of which are, non-negative because they're squares, at least one of which is strictly positive, over the integers, what comes out would be strictly positive. And so we would have an if and only if. This implication actually would hold. So we, thumbs up, check mark, we'd be done. This claim would actually be true and not wishful thinking if the sum was over the integers. Okay, the problem is this sum is actually over a finite field because G is a polynomial defined over a finite field. And over finite fields, you can actually sum up a bunch of perfect squares, not all of which are 0, and get out 0, right? Like numbers can just kind of wrap around to 0, right? Like if your field is like all integers modulo 3, then 1 plus 1 plus 1 is 0 in that field, right? So you can sum up a bunch of, like 1 squared plus 1 squared plus 1 squared is 0. You can sum up a bunch of perfect squares and get out 0. And so that is, the issue. Well, the reason this attempt 1 is wishful thinking. Okay. So questions about this? Okay, so the way we deal with this is the following, and I ran through this. I I think when I covered Spartan, but it's pretty hard to follow the first time you see it. Maybe it's not worth covering all the details, but there's something that's now just called the zero check PIOP. Okay, which exactly just like corrects this issue with attempt one. And so what happens is the verifier picks an R in 0, 1 to the 3 log circuit size at random. Okay. And up to a small soundness error, I'm going to be a little hand wavy here, a little sketchy. It does turn out to be the case that G of A comma B comma C equals 0 for all Boolean inputs ABC in 0, 1 to the 3 log S log circuit size, if and only if the equality polynomial of value, sorry, let me do it this way. Sum over A comma B comma C in 0, 1 to the 3 log circuit size, equality of R comma ABC times G of ABC equals 0. Okay. So this like gets around the issue, remember what we were looking for here was a way to relate, a way to take the property we care about, namely G evaluating the 0 overall Boolean inputs, and relate it to just a single giant sum evaluating the 0. And here we did it. And what the way to think of this, like at a very high conceptual level, without going into the details of a proof, even though the proof is not complicated, like this equality thing is by fixing like the first input to the equality thing to be this random field elements, vector of random field elements chosen by the verifier. It's like taking a random linear combination of the evaluations of G over the hypercube, right? So roughly speaking, every evaluation of G over the hypercube is getting multiplied by something like random. Okay, and we should be getting fairly comfortable with the fact that if I give you a vector of a bunch of stuff, like just some vector, and that not all entries of the vector are 0, and I take a random linear combination of those entries, I'm very, very, very unlikely to get out 0. Right, and like you can prove this formally, like with Schwartz-Zippel. And I'll skip it because we've actually done it once before, but very quickly, so it's fine if you don't remember the details or didn't follow the details. Just the intuition here is this big sum is roughly a random linear combination of all of the evaluations of G. And so if even a single evaluation of G over the hypercube is not 0, it's very unlikely that this sum will be 0, because you need some kind of crazy cancellation to happen, which is very unlikely thanks to Schwartz-Zippel, when the randomness in the random linear combination is indeed random and not chosen by the verifier, not by the prover. So that's what happens in Clover is you apply sum check to the polynomial h of a comma b comma c, defined to equal eq twiddle of r comma a comma b comma c times g of a comma b comma c. Right, and that will compute this big sum here that I'm circling in red. And to confirm that 0 indeed equals the sum over all a comma b comma c in 0, 1 to the 3 log circuit size of h of a comma b comma c. Right. That's it. That's Clover. Okay. So to summarize, what we did was we had the prover at the very start. Well, I guess I didn't say this, but so let me say it now. So let me summarize what happens in Clover. Sorry. So the prover at the very start of Clover cryptographically commits with the polynomial commitment scheme to W tilde. Okay, and is claiming that W tilde is indeed like the multilinear extension of the vector or like the gate values obtained by actually evaluating the circuit on the input, right? And so the prover's claim is true, as I explained, if and only if so W tilde is indeed the multilinear extension of the correct gate values for this circuit on this input, if and only if what I wrote above. So up to some small soundness error, this holds. So up to small soundness error, and the soundness error is coming in over this random choice of R here. So up to some small soundness error, W tilde, being assigning the correct value to every gate in the circuit is equivalent to sum over ABC in 0, 1 to the 3 log circuit size of H of ABC equals, so this whole sum equaling 0. And remember, H was defined up here. And so, so we just apply sum check to H to compute, to confirm that this is true. And now we get to kind of the rub of everything. At the end of sum check, the verifier has to evaluate H at a random point. So let's say H of R, let's say R1, R2, R3, where each of these is in 0, 1 to the log circuit size. So think of them as, they're each kind of like a gate label, but in the whole field now we've moved outside of 0, 1. So the actual gate labels are in 0, 1. Sorry, but at the end of sum check, the random values are from the whole field, not just from the Boolean hypercube. And remember, so H of R1, R2, R3 was EQ twiddle of R, comma R1, R2, R3. This R is unrelated to R1, R2, R3. This R was chosen by the verifier at random, before sum check began. It was what we fed, as the first input to EQ twiddle. So before sum check began, times, and that, G of R1, R2, R3, which, I don't want to write out for like the 5th time, but that's like add twiddle R1, R2, R3, times W twiddle of R1 minus the sum of W twiddle of R2 and W twiddle of R3. I'm just reminding you, again, I'll avoid writing it out. And so the point now is, the verifier at the end and the sum check has to evaluate H at a random point. That entails evaluating EQ twiddle at one point, which the verifier can do on its own very quickly, right? Remember, EQ twiddle is just my notate. It's just a coordinate-wise product, right? Like EQ twiddle of like x comma y is like the product over the coordinates I of x and y of like xi, yi plus 1 minus xi times 1 minus yi. So you can evaluate, the verifier on its own can evaluate EQ twiddle in time linear in the number of variables, and the number of variables here is just like three log circuit size for each of these. So in total, this is 6 log circuit size variables. So, in logarithmic time, the verifier can evaluate EQ twiddle. And then we had this discussion that for circuits with repeated structure, the verifier can evaluate add twiddle and mod twiddle at R1, R2, R3, very quickly on its own. And so that means all that's left is for the verifier to evaluate W twiddle at the 3 points R1, R2, R3. And remember, W twiddle was committed at the start. So the prover can just provide those evaluations as well as a proof that the returned evaluations are indeed consistent with the commitment. So this is exactly, we haven't covered how polynomial commitment schemes work in detail, but this is it. Getting these evaluations, these 3 evaluations of W twiddle, is exactly the point of having committed to W twiddle with a polynomial commitment scheme in the first place at the start of the protocol. Okay, so that's Clover. It's just one sum check. The sum check is applied to this polynomial H, which is just the equality polynomial times, this, weird combination of add twiddle, mul twiddle, and W twiddle. That's Clover. Okay, let me take a breath. Does anyone want to ask any questions?
I have a small one again. Very briefly, if how to say it, the commitment opening and those random points which we have 4 of in the example, are they related? Do we open the commitment in R or one of this combination of different R's or some absolutely unrelated point?
Yeah, so these are so the commitment to W twiddle needs to be, at least naively, as described here, it needs to be opened at 3 completely unrelated points. R1 in, which is in 0, 1 to the log circuit size. Field to the log circuit size, sorry. R2, which is also in field to the log circuit size, and R3, which is also in field to log circuit size. Where these values came from was, sum check was applied to a 3 log circuit size variate polynomial H. And so R1 is just the random verifier challenges from the first log circuit size rounds. So the first 1/3 of the rounds of sum check. R2 is the verifier's randomness chosen during the second third of rounds of sum check. And R3 is the verifier's randomness from the final, 1/3 of the sum check rounds. On top of that, as I mentioned earlier, many polynomial commitment schemes have nice batching procedures where you can actually provide like an evaluation proof for all 3 evaluation points at kind of the same cost as computing a single evaluation proof. And even if the polynomial commitment scheme itself doesn't have nice amortization properties, there are other tricks you can play with the sum check protocol to impose good amortization of. So basically, in practice, you're never really going to pay for 3 evaluation proofs, even though I've described things as you need 3 of them. You wind up, as far as the prover is concerned anyway, only kind of paying the time cost of computing 1 evaluation proof. But yeah, these 3 points that the sum check verifier needs to evaluate the committed, W tilde polynomial at, they're just completely random, unrelated points. Again, the first point's chosen during like the early rounds of sum check. The second point's chosen during the middle rounds of sum check, and the third point's chosen during the final rounds of sum check. Does that answer the question?
Yes, I only wonder. Does this means that does this mean that hiding property of commitment will be probably broken since we will have R as many as bits logarithmic to the circuit size, and commitment schemes usually allow for, I don't know, 1, 2, or a very few opening without breaking hiding.
Yeah, so you can. I don't think nothing really breaks here. Now you do need to design your commitment scheme to be prepared. That like so. Okay, multilinear polynomial commitment schemes. Their evaluation proofs are typically, or always really, unless you use snark composition, at least logarithmic in size, meaning linear in the number of variables. But if I give you like an L variant multilinear polynomial, like the actual size of the polynomial is like 2 to the L, because there's like 2 to the L Lagrange basis, polynomials in L variables. So, the evaluation proofs for multilinear commitment schemes are typically, at least L group elements or something like that, which is like logarithmic in the size of the committed polynomial. So you do have to design the multilinear polynomial commitment scheme, if you want ZK, like to be hiding, despite the fact that, the proof contains logarithmically many group elements rather than just 1 or 2 or 3 or 4 group elements. But you can do that, and it doesn't really add, major overhead. It sort of, everything works out fine. If you'd like, take a look at zeromorph. I'd say that this is kind of the main. I'll call it main. I mean, maybe it's not the only one, but it's like certainly the main, like, hiding multilinear polynomial commitment scheme today. And so it addresses, what I just said. Like, the proofs are logarithmic in size, but there's enough kind of random values happening there that everything gets masked, and hence is not leaking any information about the committed polynomial in the end. And then separately, you would have to make sure that the prover's messages in the sum check protocol are also not leaking any sensitive information about this W tilde polynomial. And there are ways to do that without adding too much overhead as well. But it's actually there are papers on this topic that definitely kind of brush some important issues under the rug. I know some folks who have been implementing zero knowledge snarks that use sum check, and they've run into some painful details that I think some of the papers, not zeromorph, but papers focused on making sum check hiding, have sort of not really quite grappled with. Anyway, so hopefully this is a little bit of helpful color in response to your question.
Yeah, I was totally confused with the univariate commitments. Thank you. We'll remember this thing. Thank you.
Yeah, great. Yeah, no, you do. The bigger the proofs, the more sort of randomness has to be injected to keep everything masked and from leaking any information. And the multilinear commitment schemes lead to somewhat bigger proofs than the univariate techniques. But the benefit is they have a faster prover. Yeah. Other questions?
Yes. Hey, Justin.
Hey.
I have a question regarding the use of the random variable that is sent before the sum check begins.
Mm-hmm. Yeah.
Could you clarify a little bit, because I'm confused in the sequence. I don't know if I'm confused, but I'm considering like a grinding attack or something where this random value is sent and then the prover can try different values, or is this not possible?
Yeah, so after you fiat Shamir everything, that grinding attack is definitely there. But the key is, when I said up to a small soundness error, this soundness error, so that is the probability of picking like a bad R, such that, what do I mean by bad R? I mean, G of A comma B comma C does not equal 0 for all Boolean inputs A, B, C, and yet this sum does equal 0. That's what I mean by bad R. That would be the exact kind of R that a cheating prover wants the verifier to pick. And so the probability that the verifier indeed picks this bad R, such a bad R, is just like 3 log circuit size over field size. So, if your field is, 2 to the 120, size 2 to the 128, or, even size 2 to the 256, this soundness error is so small that the grinding attack is hopeless, basically. Does that answer the question, or should I go into yet more detail?
No, it's fine. Then it's just infeasible. That's the point.
Yeah. Again, like the intuition is that taking this equality polynomial and feeding R into it, and then multiplying, the values by G's evaluations and summing everything up. It's very similar to just taking a truly random linear combination of G's evaluations. So these EQ twiddle evaluations, when you fix R and then range over Boolean ABC, they're not totally independent. So it's not truly it's not a true random linear combination, right? But it's close enough to truly random that this soundness error is still nice and small enough if you work over a big enough field to render the grinding attack you mentioned way too expensive for any machine to actually find a convincing proof of a false statement. And then the benefit of using this equality polynomial instead of a truly random linear combination is because it plays like really nicely with sum check, right? Like there's like circuit size cubed terms of this sum, and so it would like really suck performance wise to have to like pick a truly random number for each of the circuit size cube terms. So in here we can just pick R at random, which is log circuit size cube with many random values, and that's still like enough randomness to make this sum equal 0 if and only if the original thing evaluated to 0 everywhere over the hypercube up to just this small soundness error. Any other questions? No? Okay. Let me just check on the time real fast. 112. Okay, so that's Clover, and I discussed how it compares to GKR. Again, in a sentence, shorter proofs, kind of conceptually nice that there's like just one sum check. That's the benefits of Clover. The big downside is the prover commits to more data, commits to all these interior gate values for the circuit that GKR would not. Okay, and that can be expensive committing to all that extra data. That's Clover versus GKR in a nutshell. Let's talk a little bit about R1CS and how it relates to CircuitSat. And then I might or might not cover Spartan really, really quickly again. Spartan, is kind of extends Clover from CircuitSat to R1CS. So let's talk about R1CS. So in an R1CS instance, there are 3 matrices, A, B, and C, which together you should think of as like analogous to a circuit. And the prover, claims to know a vector Z. So let's say these are like n by n matrices, so n rows and n columns. So the prover claims to know a vector Z in field to the n, such that AZ entry-wise product BZ minus CZ equals 0. This is entry-wise. Okay, and if you don't like matrix notation, then I can write the constraints equivalently as follows. Let little a equal a times z, little b equals b times z, and little c equals c times z. Then these constraints are equivalent to for all I equals 1 to n, little ai times little bi equals little ci. Okay, so this is called a rank 1 constraint system. Each and every one of these is called a rank 1 constraint. Rank 1 refers to the fact that there's only one multiplication here. That's what rank 1 means. Okay. Now I often call R1CS a generalization of circuit sat. What I mean by that is there's a very simple transformation from any circuit satisfiability instance to an equivalent R1CS instance. So for example, so let's see the transformation in action. So let's say we have very simple circuit here plus, let's say plus and then times. Okay, so this is a circuit sat instance. Let's say the prover claims to know an X such that C of X equals 1. I don't know. So I'm going to turn this into an equivalent R1CS claim. So this claim is really equivalent to just a single rank 1 constraint, actually. What is the constraint? It is x1 plus x2. So that's in orange, that's just the value of this addition gate. Times, and this times is coming in from the multiplication gate at the output. And then x2 plus x3, which is coming in from this addition gate, equals 1, or whatever the claimed output is. Okay, and so that this is a rank 1 constraint system. So maybe I think my example was too simple since I made it up on the fly. Maybe it doesn't reveal the general idea. But so let me try a more complicated example. But here I took a circuit sat claim and gave you an equivalent instance of R1CS. Okay, it's not in matrix form, but you can see it's rank 1. So maybe I'll try to write it in matrix form now. Should I do that? So Z would be, I'll try to write in matrix form. Z would be the column vector x1, x2, x3. Is there? And I guess so every multiplication gate winds up getting so let's say let me give this a name. And maybe I'll call it x4. Yeah, sure. And so, right. So when you turn a circuit sat instance into R1CS, there's an entry of Z. So I will try to give the general transformation now. So there's an entry of Z for every input to the circuit and every multiplication gate. Okay. And there's one constraint in the R1CS instance per multiplication gate in the circuit. Maybe I'll write out the circuit to not get it, rather than calling it capital C, so to not get it confused with the R1CS constraint matrix that I also call capital C. And so, there's a rank, every multiplication gate in the circuit, like the requirement that it actually is assigned a value that's equal to the product of its two input gates, that's a rank 1 constraint. Yeah. So you just include, this is basically a transformation. You put an entry into the solution vector for every multiplication gate, and then you have a constraint in the R1CS for every multiplication gate, capturing that the multiplication gate indeed was evaluated correctly. Okay. And then addition gates are sort of R1CS sort of wraps the addition gates into the additions in the involved in matrix vector products. So maybe I'll just try to write this out. So in this example, I want to give you AZ entry-wise product BZ equals CZ. That's equivalent to this constraint, which is in turn equivalent to the circuit stat instance. So what A would be is so we want AZ to have one entry, and that entry to A times Z should have one entry, that entry being x1 plus x2. So what is A? Well, A just has one row, and that row is 1 1 0 0. Okay, and this ensures, so if this is Z and then AZ is x1 plus x2. So similarly, B would also just have one row, and it will be 0 1 1 0, because that ensures that BZ is x2 plus x3. Okay, and then CZ would also just has one row, and that is 0 0 0 1. That ensures that CZ is x4. And so the R1CS requirement that AZ entry-wise product BZ minus CZ equals 0 is the same as x1 plus x2, because that's AZ, which only has one entry, times x2 plus x3, which is BZ, which only has one entry, minus x4 equals 0, which is the same as saying the value assigned to this multiplication gate is the product of its two inputs. The input, the left input being x1 plus x2 and the right input being x2 plus x3. So, since I didn't prepare this, I didn't do a great job presenting the transformation, but hopefully this has given you the idea. If I have a circuit stat instance, I can turn it into an equivalent R1CS instance. In the R1CS instance, there is an entry of the solution vector for every input to the circuit and every multiplication gate. There's also a constraint in the R1CS instance for every multiplication gate. And the ith constraint just enforces that the ith multiplication gate indeed is assigned a value that is the product of the two inputs to that multiplication gate. That's it. Okay. And so, the way I think of R1CS generally is it's like an arithmetic circuit where you kind of only pay for multiplications. Yeah, because the number of constraints is independent of the number of additions in the circuit, of addition gates in the circuit. So, whether or not some snarks for R1CS have a cost profile where the additions actually do cost the prover work, and others don't. So additions are free, quote, free for the prover in Growth 16 and Spartan. At least Spartan, when Spartan is applied to circuits with repeated structure. But in Planck and Marlin, actually the addition gates do have a cost for the prover. This is getting into the weeds, but so again, the number of constraints in the R1CS instance, that's the same as the number of rows in the matrices, grow only with the number of multiplication gates in the circuit you started with. The number of non-zero entries in the constraint matrices, the R1CS instance, do grow with the number of addition gates in the circuit, and that's where the different cost profiles come in for Spartan and Growth 16 versus Planck and Marlin. In Spartan and Growth 16, the prover sort of only pays for constraints. In Planck and Marlin, the prover pays for any non-zeros in the constraint matrices A, B, and C. This is more in the weeds than we really needed to get. So just ignore what I said if you didn't follow it. So that's R1CS, and people generally consider it more expressive than arithmetic circuits, precisely because you can sum up a lot of things. And not have the number of constraints in the R1CS instance grow. And for some R1CS snarks, you don't, the prover only pays for the constraints. And so, yeah, so R1CS is kind of kind of like arithmetic circuits where you can have addition gates that sum up a huge number of other values, and you sort of don't really pay anything for summing up large quantities. Whereas in just an arithmetic circuit, if you restrict it to have Fandom 2, then like a giant sum has to be implemented with like a large number of addition gates, and then like the GKR protocol would actually pay the prover would do work, for each addition gate or whatever. So again, R1CS, roughly speaking, is like an arithmetic circuit where, you can have very large Fandom addition gates and not really pay anything for them. Okay, so that's R1CS. Let me see if anyone, I'm going to pause. Does anyone want to ask any questions about that? Nope. Someone want to just confirm that, just so I know I haven't like dropped off the call or something?
I
I'll
I have a
look.
question. Hi.
Oh, hi.
The mic was what? Hi. So thank you. So I have a question about what you said just before. So I see that the degree between the dot product is 1. So it is all the time degree 1, or to construct R1CS we must have degree 1, or we can have a higher degree. I'm talking about the variable x1, x2, x3, and x4 in this constraint. This is my question. Thank you.
Yeah, so the definition of R1CS requires that there's one multiplication. So you can take like, any linear function of the entries of Z and multiply it by any other linear function of the entries of Z. So you cannot have any multiplications like in here, right? So that means the degree is going to be, at most 2, right? A linear times a linear is a degree 2 thing. So R1CS says it's got to be linear times linear. Now there are snarks that were originally described for R1CS that, with no new ideas, go beyond R1CS and can easily handle higher degree constraints. This has actually been a major source of confusion in the literature, where there have been papers that describe a snark for R1CS, and that means people think that you need major new ideas to support higher degree constraints, when in fact you don't. It's just the authors chose to describe their snark for R1CS because it's nice and clean and simple. But anyway, the definition of R1CS says every constraint has to be linear times linear equals something. Did that answer the question?
Yes, thank you. Maybe I have just a little question. It's about if we have 2 circuits and we have 2 R1CS constraints, is there any possibility to mix the two, a linearity, for example, property, or anything like this? Or it's not possible? This is my second question.
No, yeah, it is. I mean, that's almost exactly how like Nova works. So I don't want to get too into the weeds, and I often say that and then do exactly that. But let me just try to keep it simple. So Nova, at least directly, is useful for what I call iterated computation, where you want to take the same simple function and iteratively apply it many times. So like, you take a simple f and you apply it, and then you apply it again to the result, and then you apply it again to the result of that, and then you apply it again to the result of that, and so forth. And what Nova will do is it will take an R1CS representation of f. Think of that as analogous to just like a circuit implementing f. And it will, in order to prove that f was correctly applied iteratively 4 times, what it will do is it will basically take the 4 circuits, the 4 R1CS instances, and like munch them together. So it'll like, take these 2 copies of the R1CS and like randomly combine them into one. And then it'll take this copy of the R1CS and randomly combine it with the result. And then it'll take this copy and randomly combine it with the result. And, so at the end of the day, you've reduced like many applications of F down to like one application, but it's really capturing like some kind of random linear combination of all of the original applications. This is, of course, also something closely analogous to what happens in like the GKR protocol or Clover if you were to apply it to like something like a data parallel circuit or something that applied F independently many times. I won't go into the details, but like basically the first round of sum check would basically randomly combine, pair up the copies of F and kind of munge them into one copy of F. And then the second round of sum check would take, the two resulting remaining copies of F and munge them together. And, that is what would happen if you look at applying the GKR protocol to data parallel circuits like that. It's if you squint in the right way, that's exactly what's going on. Is like adjacent copies of F are getting randomly combined in each round of sum check. So hopefully that was somewhat useful. Let me know if I should elaborate or clarify further.
Yeah, thank you. I get it. So, and another maybe last question about this point. Let's suppose, for example, we have two circuits and we get two R1CS constraints, but not of the same size.
Mm-hmm.
And let's see, we have the same Z. So can we mix the two and get another circuit which generalize the two, let's say, circuits? Right.
Yeah, people have looked at this. I don't really know what the right pointer is. So I'll follow up on that asynchronously. People have looked at like folding schemes where you're folding different circuits together. So I think there is something you can do there, but I'll have to offline find the right pointer for you. So I'll put that in the Discord soon. Put it that way.
Okay. Thank you. Because I was trying to do it for two small circuits, but I didn't get it how to do it. So this is why.
Yeah, I mean, what I can say briefly, because I'm much more of an expert on like sum check based on arcs than folding schemes. So I'm gonna ping an expert, query an expert oracle about the folding scheme. So what I can say is, if your question, if you think about applying the GKR protocol or Clover to your question, what's going on is like you have a circuit C, which is claimed, to output some Y on input X, and then like a different circuit, which might be a different size as well, C prime, which is claimed to output, some Y prime on some input X prime, right? And what you can do is you can apply GKR, or you can treat these as one big circuit with, so you just treat it as one big circuit, C prime prime, which, is like C prime, and the input to C prime prime is like the concatenation of an input to C and an input to C prime, and the output is the concatenation of an output of C and an output of C prime. So you can apply GKR or Clover to C prime prime, and then where the added complexity that this C prime prime actually has two like unrelated parts comes in is like if we're dealing with Clover, like the add twiddle and mult twiddle polynomials for C prime prime, well, it's sort of just an amalgamation of the add twiddle polynomial for C and for C prime. And so it's just all you've done is made add twiddle and mult twiddle a little more complicated. So actually, to write this out really briefly, again, I will keep this to 30 seconds. Like the function for C prime, every gate is just going to have one extra variable in its label, and this variable is going to tell you, are you in C or are you in C prime? So 0 is going to mean I'm in C, and 1 is going to mean I'm in C prime. And so I don't want to completely write this out, but maybe let me do it this way. Lost my eraser, whatever. So just waving my hands wildly, like basically the add polynomial for C prime prime will be like X, 1 minus X0 times the add polynomial for C, plus x0 times the add polynomial for c prime. And what's going on is, if x0 is 0, then this evaluates to 1 and this evaluates to 0. So you just get out, the add polynomial for c. And if x0 is 1, then the first term dies because 1 minus 1 is 0. And the second term, the x0, spits out 1, and you get the add polynomial for c prime. So, the folding situation should be analogous where, you can take two unrelated circuits. If you want to prove something about both of them at once, you just lay them side by side, treat them as one big circuit. And all you've done really is the only thing you pay for that is you've kind of made these wiring polynomials, more complicated, sort of net. It's sort of the complication is like it's now like the sum of the two rather than each of them individually. Anyway, hope that's a little bit helpful.
Yes, very nice, really very nice, because it reminded me of the Lagrange interpolation of circuits at this point. It's not
Exactly. Yeah, you are.
field elements, but Lagrange interpolation of a lot of circuits.
Yeah.
Very nice. Thank you.
Yeah.
Nice idea.
Yeah. Thanks for the question. Okay. Other questions?
Professor, I had a quick question. So the composition that you're showing in this figure, in the red figure, let's say this is figure 2, the composition that was there with respect to Nova in up a little bit.
Up a bit.
Yeah. There was a FF composition that was in green.
Okay.
Let's call this figure 1.
Uh-huh.
So I can convince myself, maybe I'm missing something. I can convince myself that the composition in this figure 1 is this for arbitrary circuits. Then I'm not sure whether this composition is closed for arbitrary circuits, or are we talking about some subclass like NC1. But I can totally, you were claiming that the lower figure 2 composition is closed for any arbitrary circuits.
Yeah, so this figure 1, so F can be arbitrary, but the folding scheme, like in at least the original Nova paper, what gets folded is just like iterative applications of F. So the scheme is sort of only directly useful for functions that you can write as iteratively applying a relatively simple thing over and over and over again. So if you had a computation that just cannot be decomposed into iterative applications of something simple, then Nova itself wouldn't directly apply, although sometimes there's some nice gymnastics you can do to take something that's not obviously decomposable in that way and make it decomposable in that way. Whereas this thing is more general, where you can just take like a bunch of unrelated circuits and just stick them side by side and treat them as one giant circuit. But of course, if you had, the giant circuit is still, like describing 1,000 different circuits laid side by side. I have to tell you what the 1,000 circuits were that I laid side by side, and that so like the wiring of the giant circuit is sort of more complicated and therefore more expensive for the snark verifier to deal with. The more things you're laying side by side, the more different things, right? So like if I laid the same C side by side with itself like 100 trillion times, like all I need to describe that circuit is I need to tell you C and I need to tell you 100 trillion. That tells you I'm talking about C laid side by side 100 trillion times. But if I lay 100 trillion completely different circuits side by side, I have to tell you each of those 100 trillion circuits. And so the description size of the circuit just gets much bigger, and that gets reflected in this add twiddle and mul twiddle polynomial getting more and more expensive to evaluate. Was that helpful?
So I just wanted to make sure that I get correctly that so figure 2 is closed under composition, but figure 1 might or might not be for arbitrary class of circuits.
Under composition, I guess it depends what you mean by composition. What I would say is like this technique I described here
Mhm.
is more general than Nova. Like this captures, like proving correct evaluation of an arbitrary series of circuits. But if all of the circuits in the series are completely unrelated, there is some cost to that. Whereas Nova, as in the original Nova paper anyway, is sort of specific to repeated application of the same simple circuit over and over again. But there's been a bunch of follow-up works that kind of, generalize Nova in towards this direction. But I'm going to have to go and query an Oracle regarding just how far they've gotten in terms of ability to support many different simple circuits getting applied rather than the same one over and over again. Was that a clear enough response?
I think I'm not being able to articulate the point of composition of circuits as we know in maybe algebraic complexity or something, but it's okay.
Okay. Thanks for the question. Yeah.
So, looking at this picture, this scheme that you're having in front of us now, am I correct that it is kind of a variant of the technique that you showed us in the very beginning, where if C prime needs to use, for example, a result of C of the left part of this composition, then it can be idle for the needed number of rows in C prime, and then just steal from its neighbor.
But
Steal
I
the
didn't
value.
quite the question was like, what if some of the inputs to C prime have to equal what the outputs of C or something? Was that?
Yes.
Yeah. So that right, and so Nova is to be clear, I guess that is the situation Nova is interested in. So same C over and over again, but like the output of one copy of C is treated as the input to the next copy. There are ways to deal with that, but it can be a little nasty. Is the short answer. So the picture I drew here before I just edited it was just completely independent inputs to C and C prime. Then life is very easy and simple. If you want the output to C to be part of the input to C prime, there are ways to design snarks that force that to be the case as well, but it can be a headache to do. I think that's the most I want to say about that right now.
Okay, thank you.
Yeah, well, it's a good question. People who have worked on folding schemes for a long time have remarked on this that the details of sort of making sure that like outputs of and inputs link up correctly are just like brutal if you really go all the way down deep into them. And similarly with sum check based snarks, it's just can be very piddly. Yeah. So but typically, if you suffer enough, you'll find a way to enforce that without a major increase in costs or whatever. I'll just leave it at that right now. Okay. Other questions? All right. So all right. I guess I'm gonna try to do the following two things. So one is so I want to now give a counterpoint to this framing of R1CS as a generalization of circuit SAT. Okay, because really they're incomparable. Okay, and so I said like you can take any circuit SAT instance and turn it into an equivalent R1CS instance. The reverse is also true. But the circuit that comes out is actually very simple and silly, where you just have, so what is this transformation? Like let's say, let's say the R1CS has two rank 2 constraints. So that, let's say we have this constraint and this constraint. So if I turn this into a circuit, I'm just going to create one gate for every one output gate for every constraint, and I'm going to insist that all of the outputs are 0, right? So I'm just going to compute the the left hand side of each constraint like in the circuit. So for this constraint will turn into the first constraint will turn into the following, which is literally the circuit we had before. But I guess now let's see. I guess I would need a subtraction gate too. Okay. And then then there'd be a multiplication gate that's multiplying x1 and x2, and then a subtraction gate that is subtracting x3 from that. Yeah, so I just like compute the left hand side of each R1CS constraints in the circuit and claim that all the outputs are 0. Like that's it. And so the reason this is silly is like every output gate has degree 2 now. Like if you look at the expression computed by each output gate, because you started with rank 1 constraints, each constraint involved only one multiplication. You just have like a ton of very low degree output gates of this circuit, right? So this is like very much not leveraging the full power of arithmetic circuits, right? In general, like very small arithmetic circuits can compute very complicated, like very high degree functions, right? Like here's a little extreme case where I have like a size D circuit, and it computes x1 to the 2 to the d. So with depth d, size d, I can circuits, I can compute functions of degree 2 to the d. So arithmetic circuits are very like good in the sense at computing very high degree functions. And like rank 1 constraint systems by definition just don't even consider high degree things. So really, while I often so I guess I've like kind of helped create the problem. I often call R1CS a generalization of arithmetic circuits. They're actually really incomparable, right? R1CS is sort of more general than arithmetic circuits because in R1CS you can sum up lots of things like without adding more constraints. But on the other hand, R1CS is inherently restricted to low degree, while circuits are like, with very few gates can compute very high degree things. Okay. And so, I'm just going to briefly remark without saying more now, like a couple years ago, people were very surprised to find that some check-based snarks could like prove very high degree constraints relatively efficiently. And in fact, they should not have been surprised. And not only that, but like the way some of the results that were shown are like not even close to optimal. And the reason they're not close to optimal is because if you do have a very high degree constraint like this, involving something like this, right? The best way to prove it is with the GKR protocol. So like there are results that if you have a high degree constraint like this, will wind up arithmetizing the whole circuit all at once, and thereby sending like a degree, like it'll apply some check, but in each round the prover will send a degree 2 to the d polynomial. If and this is probably the best you can do if you only use just one or two invocations of sum check, right? But if you use the GKR protocol, you sort of can break something very high degree into a series of sum checks, each one getting applied to something low degree, just like a degree 2 multiplication gate or something. And in that way, you can keep, all costs, roughly order D rather than 2 to the D. So, at a high level, I guess what I would say is, R1CS is kind of more expressive than arithmetic circuits because you can sum many values up at once without adding constraints to the R1CS. On the other hand, circuits are really nice at computing very high degree things, and especially if you apply GKR to prove that you evaluated the circuit correctly, you can avoid paying really much for the degree in either prover cost or proof size. Okay, so hopefully that little discussion there was worth the 2 or 3 minutes it took. And now I'm just going to very briefly sketch Spartan for R1CS. Again, Spartan applies directly to much more general constraint systems, but it's nice and clean to describe for R1CS. That's how it was originally described. Okay, so let little a equal a times z, little b equals b times c, and little c equals c times z. And so the prover, in R1CS, the claim is that AI times BI minus CI equals 0 for all constraints, for all entries I of A, B, and C. Okay, and so, we said before that up to some small soundness error, if V picks an R at random, this is equivalent to the sum over, and now we're going to index entries of A, B, and C by binary vectors like usual when we apply sum check. So the sum over